Okay, so I'm going to start with some of the questions that I got from, I believe it's homework 17. So it's textbook questions and it's the ones on convergence and divergence. So similar to the castle attack that we did today. So determine the convergence or divergence of the series 6, 8, and 12 were the questions that someone asked me about. So for this particular one, you guys have so let's talk about number 6. This is an important one. So when you're doing alternating series, whether or not to move on to AST or not depends on your series. So every single series that you guys start with, you should take the absolute value first. And if you're going to be able to prove that it diverges by the nth term test, then you do not need to move on to AST. So I'll say that again. If you guys take the absolute value, which when we do in this case, we end up with n over 3n plus 2, and we observe that the limit as n goes to infinity of this is equal to 1/3. So let's say a sub n is our general term, and we get 1/3, then that means that since it's not equal to 0, we can say that this is divergent by nth term tests. And we don't want to move on to AST in this instance because AST only can be used to show conditional convergence. So if it's divergent, we want to be able to prove divergence through another test, either nth term test or a ratio test or some other test. Now, if you end up with a p-series or a geometric series, whether it's LCT to either one of those, then and it ends up diverging at this stage after you're testing absolute convergence, that's where you want to move on to AST, because AST will always pass the conditions for both geometric and p-series. So 6, this is all you guys have to do. You do not have to do AST. Number 8, when you guys take the absolute value of this, you end up with, so I'm going to say, we're going to test absolute convergence first by taking the absolute value of it. And then what we end up getting is a geometric series. So another thing you guys want to be aware of is that 1 to the nth is the same thing as 1. So we can also rewrite this as 1 over e to the nth power. So therefore, inside the n umbrella, you guys have a common ratio. And that common ratio is between 1 and -1. So therefore, by geometric series, this is absolutely convergent. So since it's absolutely convergent, this means that this series has a strong convergence. So there's no need to move on to test AST, because AST is kind of like worst case scenario. If it's not absolutely convergent, then we can possibly show that it's conditionally convergent by doing AST. But if it's already absolutely convergent, then we just can stop our testing there and then say absolutely convergent by geometric series test. Number 12. So there's the one that I find is the trickiest for students is the ones with ln of n, because depending on what you guys have for the exponent of n in the bottom, it could result in a variety of different tests. So in this instance, after you guys take the absolute value here, you're going to end up with, and we saw this one on, I think, a couple of different assignments, including the castle attack. But with this one, since you guys can do this one in 2 different ways, and either way is okay. So if you notice, this is something that is integrable. So one method would be to apply the integral test for that. And just as a refresher for the integral test, you guys are going to integrate, and feel free to switch your n's to x's and integrate from 1 to infinity. Keeping in mind that if you guys do the integral test, since we're talking about infinite series, then the work for this would involve changing it to an improper integral and changing that to b going to infinity and 1 to b. I'm just going to let you guys do this integral test on your own, but if you end up with something that is finite, your conclusion for the integral test is that it behaves the same way. So therefore, your series is also divergent. If you guys get a finite answer using the integral test, then our conclusion is that our series is convergent. Please note that if you guys get a finite answer, it doesn't mean that that's the sum, or the answer to the sum of the series is that answer that you guys get for the integral. So that's one way to do the question. So another way to do the question is through DCT. Let's see if this one works. So if we're trying to compare DCT, and I know that ln of n happens to grow faster than 1, then I know my inequality goes like opens to the left, where ln of n over n must be greater than 1 over n. And since I know that this is a divergent p-series, and so if you're doing your arms, the divergent p-series is under, so it pushes the function that is above upwards as well. So our conclusion is that by DCT to a p-series, so just a refresher, as you guys were doing the castle attack, I noticed that the work, you just said DCT, and then you might have just said to a p-series, but don't forget that DCT requires the inequality stated, verify that that's true, because sometimes your DCT can fail, or integral tests show your work means that you guys have to actually integrate, and then LCT, you have to show the limit is equal to a constant value. So in this instance, after showing the inequality, you would state by DCT to a p-series. And I'm not sure if I mentioned this enough. You guys can say p-series 1 over n is divergent, but this is a famous p-series, the one that is the first one to diverge, or the closest one to being convergent. It's like kind of the borderline. This is called a harmonic series. So a lot of times on the scoring guides, you guys will see, they'll say it's a comparison to the harmonic series, and that's just the special case of a p-series where n is equal, or sorry, p is equal to 1. So it's the special one. So that completes that side of homework, I think 17. And then the person also had questions on 49. And so for 49, it still asks whether it converges, but this time it does ask you if it's absolutely or conditionally. So I'll mention something that is oftentimes confused on the homework assignment, or sorry, on the castle attack as well. I saw some mistakes on that. When you're performing this, anytime you guys see a factorial, in our notes, I did make sure to mention that if there's a factorial that you guys want to do the ratio test on it. And in doing the ratio test, I noticed that I don't have an x in this, so this is not finding the interval convergence. It's just stating whether that particular series is convergent absolutely, conditionally, or diverges. So we move on to the ratio test. When I apply the absolute value, it's going to take care of the alternating part, which is the -1 to the n. And then I'm going to plug n plus 1 in, making sure that I put it inside the parentheses. That's important because it's a quantity. Factorial times the reciprocal of your nth term. Okay, and then we're gonna just practice simplifying your factorials. 2n plus 1 factorial is 2n plus 1 times 2n plus 1 minus 1 is 2n, and then 2n minus 1 dot dot dot. And then on the bottom here, you guys have 2n plus 2 plus 1, so 2n plus 3. So this ends up being 2n plus 3 times 2n plus 2 times 2n plus 1 dot dot dot. So for this particular one, only the 2n plus 1 factorial gets canceled with the bottom, and your limit ends up being as what you're asking yourself, what happens when n goes to infinity? Well, you've got n 4n squared on the bottom as the highest power leading term. And so if you let the bottom go to 0 and the top is just 1, then our answer, sorry, not to 0, but to infinity, we get 1 over infinity, or essentially 0. Please note, we're not solving for x. So at this point, we would just observe that since it's less than 1, we would say that this is absolutely convergent. Because it's absolutely convergent, we don't need to move on to AST because absolute convergence is stronger than a conditional convergence. On the AP test, one thing I also wanted to emphasize is that if they ask for whether or not something is convergent or not, It doesn't matter if you guys show if it's conditional or absolute, either one results in convergence, so it doesn't matter which one. So for 50, 50 also is one particular series and not solving for it in interval, and please note there's no x's in it to begin with. So in taking the absolute value of this, you guys observe it's similar to, so you guys are going to think, what is it similar to? It's similar to 1 over square root of n, which is 1 over n to the 1/2. Because you guys have something added to the 1 over square root of n, then this means that it's going to involve a comparison test. So if it's a p-series, we're going to want to use LCT if we have the option, because then we don't have to establish the inequality. So in this case, showing the work for LCT involves that you guys stack one of the original series, absolute value of it, with what you're comparing it to. When I flip, change and flip, I end up with square root of n over square root of n plus 4. Ratio of leading coefficients equals 1. Since this is a constant, then I can conclude that it behaves the same way as the series I'm comparing it to. So for this one sentence, if you guys had to write a free response, you would say by LCT to a p-series, name the p-series, because that p-series diverges, then your series that you're comparing it to also must diverge. Now, all of this is just for absolute convergence or not. If you guys are doing a free response and this ends up being like an endpoint, then you can just say LCT to a p-series. Don't have to show the limit. This is only if like that series alone is the problem. But if it's an endpoint, I feel like they're a little bit more lenient on grading what you write out. So for sure you want to mention LCT. For sure you want to mention what you're comparing it to. And then from there, we do have to move on to AST. So if at any time you guys get that it's not absolutely convergent and it was a p-series, whether it's a comparison to or the original p-series, geometric series, or a comparison to a geometric series, those two types of series will pass AST. So at this point, we would move on to verifying that the n plus 1 term, which when we increment n plus 1 and add 4, we get n plus 5, that the n plus 1 term is less than the nth term. This is true. Adding 5 to the bottom will make that a smaller fraction, as well as taking the limit as n goes to infinity of your general term. No, please note that I'm doing 1 over square root of n plus 4 and not just 1 over square root of n, because sometimes people revert back to the p-series that they were comparing it to. You want the general term of your original series, and we want to verify that that essentially that it decreases to 0, or that the limit of the nth term is equal to 0, which it does. So for this one, we would conclude that this is conditionally convergent. So these types of questions that I just did could end up being one of the endpoints. And this is the type of analysis you guys would have to do for finding if your original series started off with an X and then you got down to testing endpoints. This might be the results of one of your endpoint analysis, just one of these problems. So I don't know if more questions are coming in or not, but I'm going to address some of the other questions that came up, including back to the review assignment. I'm going to do one of the more complex. I can't remember which one it was now. I just erased all the work for it. In the chat, is there anyone that wants me to do anyone in particular from the 1 through 8, which might be useful for you guys to do on, I'm thinking it was it number 3 or number 4 that might have been challenging, and then I'll jump to multiple choice, I think, or the AP Central multiple choice. Let me see which one it was that we had a question on. There was one where it results in just odd, and so it's not alternating. Okay, I'm just gonna take a guess, and I think it was number 3. It's either 3 or 4. Okay, we'll just pick one to do. All right, so we start. So I want you guys to think about the questions I just did and this one. So this one is different now in that we have to solve for an interval, and you'll notice that there's an x in it. Because you guys have things that have n's in the power and n's in the base, then we know that it's complex enough that we're going to apply ratio test to this. And then automatically, if we're applying a ratio test, we know we have to test endpoints if we're solving for an interval. So in taking the absolute value, it's going to take care of this part of it that makes it alternating. And then, so I'm going to enclose the 3x minus 1 inside the absolute value bar, and then raise it to the n plus 1 power, n plus 1 squared, and that's my n plus 1 term. I'm going to multiply it by the reciprocal of the nth term, so n squared, 3x minus 1 to the nth power. We're going to circle this, reduce it by the nth. So then we have just 3x minus 1 absolute value of that to the first power when we subtract n. And then the secondary thing that we're going to reduce is, observe that this is growing at the same rate. So therefore, ratio of leading coefficients is 1. So then we end up with 3x minus 1 absolute value must be, this is what the ratio test is. And according to ratio test, we must show that this is less than 1. So we end up with 3x minus 1 is between 1 and negative 1. And then when we add, we end up with 3x is less than 2 is less than 0. Divide by 3. X is less than 2/3, 0. So just a quick comment of how the question is phrased here. It's asking you guys to find whether or not, let's see, the radius of convergence. So let's start with that. The radius of convergence, I wasn't able to catch third period's mistake on finding the radius of convergence by adding, but I'll just mention it here. I know it doesn't really make sense with this problem, but whenever you guys are finding a radius of convergence, don't forget that you're finding the difference between a and b, not the sum of, and then dividing it by 2. So 2/3 minus 0 divided by 2 is going to result in a radius of convergence that's equal to 1/3, or it's half of that, the length of that interval. Okay, so let's talk about the difference between what they're asking for you guys to find in B, C, and D. So the interval convergence is currently 0 to 2/3. So what I will say about this is, because you guys took the absolute value at the very start, then the answer that I got means that every interior value of this interval between 0 and 2/3, including 1/3, results in, it results when I plug it into x, into the original, in an absolutely convergent series. So there's technically an infinite number of numbers between 0 and 2/3, for which if I pick that value, plug it back into here, it's gonna spit out a series that is absolutely convergent. The conditional convergence part can only occur at 0 or at 2/3. So we go on to test whether or not it's conditionally or absolutely convergent by plugging the values of the endpoints back in. So let's say I plug test x equals 0. When I do that, I'm going to go back to my original series and then rewrite everything as is, except for with x plugged in. So -1 to the n minus 1. When I plug in 0, I end up with -1 to the nth power, all over n squared. Okay, so this was the problem I wanted to do. All right, so -1 and -1 is the same base. So when I combine this is where we want to be careful on the test. We end up with -1, and then we're supposed to add like terms. or sorry, not like terms, we're supposed to add the powers when we combine it with the same base. So 2n minus 1 all over n squared. So I'm just simplifying. If when you guys plug in the endpoints, it doesn't simplify out or things don't cancel out, then there's something probably wrong with your interval or the values of your interval. So at this point, please make sure that you guys do this extra step. Take the 1 and plug it in and see if this, what does negative 1 to the 2n minus 1 actually do? So if I plug 1 in, I end up with 3. If I plug 2 in, if I plug it in 1, I end up with 1. If I plug in 2, I end up with 3. If I plug in 3, I end up with 5. So what I'm observing is that all of my powers, when I plug it in, the index and then increment it, is resulting in an odd power. So this actually could be simplified further to say that I don't really need the 2n minus 1. This is just negative 1 over n squared. So from there, we take the absolute value because technically when we're testing, we should be testing for absolute convergence. And the result of taking the absolute value is the series n equals 1 to infinity of 1 over n squared, which is absolutely convergent. So therefore, when I go back, I'm going to include 0 and say that it's 0 also happens to be absolutely convergent. So when you're asked above about, the difference between absolute conditional, right now I'm saying every single value between 0 and 2/3, including 0, is absolutely convergent. So then we'll check next, x equals 2/3. On the AP test and on your test, you guys don't have to worry about this level of detail in terms of like the interval and then what part of it is conditionally or what part of it is absolute. You just include the values if whether it results from conditional convergence or absolute convergence. So let's try 2/3. So when I plug 2/3 back into, again, the original, n equals 1 to infinity, negative 1 to the n minus 1, 2/3 when I plug it into here is going to result in 2 minus 1 to the nth power. So then that's 1 to the nth, all over n squared. Okay, so here's another part that I get a lot of questions on, like trying to combine negative 1 and 1 to the n. So a couple things, negative 1 and 1 don't have the same base, so it's not like you guys can add the exponents. And more importantly, 1 to any power is just 1. So you guys can automatically just cancel that part out because 1 to any power is just 1. And so that what you guys have left is just this part. So you want to assess, okay, when I plug in 1, I get 1. When I plug in 1, I get 0. When I plug in 2, I get 1. When I plug in 3, I get 2. So it is switching off between or jumping by ones, which means that it does result in an alternating series. So now when I take the absolute value of this, because this is 1 over n squared, it still results in something that's absolutely convergent. So I'm sorry, I didn't say the reason in the testing x equals 0, but it's absolutely convergent by p series for both x equals 0 and for x equals 2/3. And so when I go back to include it, and then I look at the way that they phrase the questions above, it's like, where is it absolutely convergent? For this particular one, it's all of the values between 0 and 2/3, including 0 and 2/3, are absolutely convergent. There are no conditional convergent points here because any of the endpoint or both endpoints ended up being absolutely convergent. Okay, so nobody asked, but I just want to mention that when you guys are taking a look at exercises 9 through 11, the series is the value of a Maclaurin series of f of x at a particular point. What is the function and what is the point? And then what is the sum of the series? So the sum of the series is, remember I talked about like there's two variations of every function now. There's the function representation, there's the series representation, and the series representation also happens to be the sum. So if you guys take a look at number 10, you'll observe that it goes from pi to pi minus pi cubed over 3 factorial. So I should emerged that you recognize that as the sign of X Maclaurin series, and in place of X, it looks like pi was plugged in. So in theory, recognizing the function is sine of X, but after that, we're plugging pi in for all the X's on the left, so we should do so on the right as well. So sine of pi happens to be 0. So the sum of that series is also equal to 0. So interchangeable when we talk about the function and then the sum. Any other questions on this review before I move on to, let's talk about this bottom one. So like I said, the tricky questions are these ln of n ones. So let's say that you guys, I'm gonna do what most people did in this problem first and just show you guys what the mistake is, or sorry, not what the mistake, but what the problem is. So let's say that you guys tried to do what we did on the previous example where I did DCT, and you observe ln of n and 1 over n cubed. And you thought, oh, okay, well, I can compare it to 1 over n cubed because I'm just going to use the exponent at the bottom being the same. I know that ln of n is greater than 1, so I can establish this for DCT. But the problem is that I know something about 1 over n cubed, and I know it converges. So do your arm motion if you guys aren't sure. But if 1 over n cubed converges, it's below the other function that I'm trying to make a conclusion on. So technically the top function can either diverge or converge, right? So this is an instance in which it fails. So one of the things that has shown up on a couple of problems is the comparison of ln of n versus n. And so if you're not sure of which one grows faster, just real quick, looking at it just graphically, ln of n does this, and then 1 over n is, n is just x. So doesn't seem like it would be true, but the y equals x grows faster than ln of x. And let's say you guys are not sure. So anytime you guys aren't sure of the relative rates of growth, you can always apply a limit to it. So keep in mind, I'm not doing LCT, I'm just applying a limit to determine whether n is growing faster than ln of n. And it doesn't matter which one you guys put above the other. It's just whatever two functions you're trying to compare the relative rates of growth for, so you can establish an inequality. You just stack one on top of the other. When I plug infinity in, I get infinity over infinity. So technically L'Hopital's rule, which results in 1 and 1 over n, which when you guys simplify that, it ends up being infinity, right? 1 over n. Keep the top as 1, flip it to be times n, and we get infinity as an answer. What this tells me is that I should go back to my original limit, and infinity means that the top function is growing faster. So then I know that ln of n is greater, n is greater than ln of n. Now, if that's true, then perhaps instead of comparing ln of n over n cubed, I could compare n over n cubed, because I know something about n versus ln of n. Okay, so if I reduce n over n cubed, it's going to result in 1 over n squared. And so that's where the 1 over n squared comes from. And since I know that this is greater, that n is greater than ln of n from all the work that I did on the right to verify, and I know that 1 over n over n cubed results in 1 over n squared, and that this is convergent, then therefore the series I'm comparing it to also must be convergent by DCT. So kind of a trickier one because it wasn't immediately apparent with the 1 over n cubed. Please note we can't do integral tests on it because we can't integrate that, and we can't apply LCT to it as well. You guys are being really quiet with the chat and questions. I'm just trying to see if there's any other questions before I move on to AP Central.
Could you go over number 7 on the review?
7 on the review. Let's see. Yes. Okay, so 7, we have factorial. We have an x. So I know that I can't do geometric series tests on this one because you've got factorials, and then plus you've got n in the exponent here. Well, mainly because you guys have the factorial, you have to use ratio tests. So let's see, when we do ratio tests, we're going to increment by +1, n plus 1 factorial to the n plus 1, absolute value of x 2, and then n plus 1. And actually, let me move this up a little bit so that it's in the, I like to put everything that is in the denominator, or sorry, in the numerator on top, and then switch colors to times by the nth term. So the nth term, we've got the 2 to the n that was in the denominator is now on top, and then n factorial on the bottom, and then x, absolute value of x to the 2n on the bottom. And then we group things together. So let's do the 2's. When you group the 2's together, these cancel out so that you guys have 2 on the bottom. When we group these 2 together, we get absolute value of x to the 2n plus 2 is subtract 2n from that, and we end up with absolute value of x squared on top. And then lastly, the factorials. We have n factorial will cancel with n plus 1 factorial to just have n plus 1, because n plus 1 factorial is really n plus 1 times n factorial. So let's gather everything that we have. And this time with the factorials, I would highly suggest that you guys simplify and keep the limit there, because the limit, in cases with factorials, we do have to consider the fact that we're going to end up with an n or n plus 1 left over. And remember that the limit is being applied to the n and nothing to do with the x, right? So as we let n go to infinity, we're going to get an infinity on top, and our answer ends up being infinity. So now how do we answer this question? So on the questions that I started the text from the textbook at the beginning of the session, there wasn't an x in it, and there were some problems that had factorials. So for those types of questions, if you got infinity as an answer, you would just say divergent by ratio test. But here, since you guys are trying to solve for a value of x, the worst case scenario for an interval is that it's divergent everywhere except at the center. So in this case, that's what happens, is that it only converges at the center. And we only say that when we're trying to solve for x. So converges at center, which is x equals 0. We also know what the center is because there's no shifting that occurs to the x. Lastly, when you guys let n go to infinity, we're saying that it doesn't matter what values of x we use. Since n is going to infinity, this is always going to be infinity no matter what x is. So it's going to converge only at the center, x equals 0. You guys should see something like that happen usually when you guys have factorials and you're trying to solve for x. The other, and I don't know if there's an example on here where that occurs, is if your factorials had been reversed, and say your original problem had the factorial on the bottom instead, what's going to happen is that you're going to have the cancellation occur with the factorial, but the n plus 1 would be on the bottom. And so if you let n go to infinity, you're going to result in an answer that is 0. And so that one is, if you get 0 as an answer, when you're trying to solve for x, well, 0 is always going to be less than 1, and it doesn't matter what x is. So for that special case, it's going to be converges for all real numbers. So that's the other special case. Okay, so for AP Central, there was a question on, and I think a lot of people probably haven't gotten to it. Sorry, they have the answer on here. Let me erase this. Okay, the question was on 15. I think I might have recorded some videos. I'm not sure if the video was on number 15, but there are some AP Central questions from last year that I remember people missed a lot. So this one's unlike any of the other ones from above. This one's an interesting one because at the very beginning of when we first learned series, like the very first video you guys talked about, I talked about the definition of a series being a sequence of partial sums. So in this problem, it talks about an alternating series, so that's something we want to keep in mind. For -1 to the k plus 1, and this notation here is just to say that a sub k is that's like the general term, and that part of it could be anything. For example, like if I put a sub k, like what I did today on the free response, I might have had like a sub n is equal to n plus 2 over n factorial and all of this other part to it, but for this particular problem, it doesn't matter what it is. So it's just part of the general term. We see that it's got the alternating piece, and then don't be thrown off. The AP test also uses k as an increment instead of what we've been using, which is n. So if it makes you more comfortable, you guys can switch that to n as well. And so it says it converges to S, which is a sum. And that you guys know that the n plus 1 term is less than the n term. That's what that says for all values of k. The table above shows values of the partial sum for 4 values of n. If S sub 8 is used to approximate the value of the series, what is the alternating series error bound? Okay, so partial sums, what that means is that this is, if I had 7 terms, for example, a sub 1 plus a sub 2, let's say I had all of the terms up to the 7th term, the sum of all of this is S sub 7. Okay, and then if I had a sub 1 plus a sub 2 all the way up to a sub 8, the partial sum is S sub 8. So these are the values that you guys see here. So now if it says that S sub 8 is used to approximate the value of the sum, that means that 8 terms were used to evaluate the series. And so if they want us to figure out what the alternating series error bound is, the alternating series error bound would be one more than where it was that we truncated it. So 1 more than 8 would mean that it would be 9 terms. So if I went all the way to the 9th term and I added all those terms together, then I would get the partial sum S sub 9. Okay, now if I wanted to figure out what the alternating series error bound is, the definition is that it is the first term that's left off. So I highlighted it here, it would be a sub n. Okay, so to figure that out, if you think about what you guys have here, all the partial sums leading up to for S sub 8 is a sub 1 through a sub 8. So up to S sub 9 is a sub 1 through a sub 8 plus the a sub 9. So to figure out what a sub 9 is equal to, we would find the difference, S sub 9 minus S sub 8. So if we look at our chart, we have 0.5459 is S sub 9, that's the partial sum, minus 0.157. And that's going to result in the 0.302. So I think in terms of your test, I'm not going to put anything like that on there. In fact, this is kind of one of the only questions I see on the practice exams for AP Central. But that's the idea behind the partial sums and how you would use that to figure out what the necessary term is that represents your error bound. Your error bound is always going to be one more. And the information that was given to you guys kind of in notation up above here is describing just that sentence that I wrote up when we did the free response, where we said that the terms are decreasing in absolute value to 0. So the decreasing part and then to 0 is necessary for us to be able to apply the alternating series error. Also, please note, it does say alternating series error bound and it doesn't say Lagrange error bound. Error is not a huge deal on your test. I would say look at your free responses that we did today and then the Lagrange error bound that we did on the quiz. And I think you guys should be fine in terms of error. Instead, focus on interval convergence, the Taylor series type questions where you guys have to build a series. Look back at your Maclaurin series, and then radius of convergence, interval convergence, testing endpoints, making sure you guys get that practice in before tomorrow. Okay, guys, so if there's more questions that you have, please text me on Remind. I might, if you guys feel like you need it, go over more stuff tomorrow, but just let me know and then I'll let you guys know if we end up having to do a second Zoom. I think you guys will be okay, but let me know if you have more questions. I also will leave the video on there from last year's recording. So if I do extra problems on there that I didn't do this year, you guys can go back and look at that as well. Okay, guys, good luck on studying today. Bye. You're welcome, guys.